The year 2025 was supposed to be a year of drought in California. Every climate model said so. Every historical pattern pointed to it. Scientists, water managers, farmers, they all prepared for it. Dry winds, empty reservoirs, fire bans before spring even started. Instead, the skies opened. Storm after storm hammered the coast. Rivers burst. Mudslides swallowed highways. Los Angeles, a city that averages about 15 inches of rain per year, was drenched. And the reason it wasn't supposed to happen was La Niña. La Niña is one of the two phases of a climate system so powerful it controls the rainfall, drought, and temperature of nearly every country on Earth. It has operated on a predictable rhythm for as long as humans have been farming, fishing, and building civilizations around weather patterns. And right now, it is not doing what it's supposed to do. That's not just a curiosity, that's a warning. To understand why, you need to understand the machine. Beneath the surface of the Pacific Ocean, the largest body of water on this planet, there is a slow, massive engine running constantly. It's driven by wind, temperature, and the rotation of the Earth. And roughly every 2 to 7 years, that engine shifts gears. During normal conditions, trade winds blow steadily westward across the tropical Pacific. They push warm surface water toward Asia and Australia. On the other side of the ocean, along the coasts of Peru and Ecuador, that warm water being dragged away allows cold, deep water to rise to the surface. The atmosphere above follows. Rainfall patterns lock in, monsoons know where to go, farmers know when to plant. Then the cycle flips. El Nino is when the trade winds weaken or reverse. Warm water that was piled up near Australia sloshes back east toward South America. Sea temperatures in the central and eastern Pacific spike. The jet stream relocates. Droughts hammer Southeast Asia, floods punish Peru, and global temperatures rise sometimes sharply. The 1997 to 98 El Nino added so much heat to the atmosphere that it remains one of the most destructive climate events in modern history, responsible for over 35,000 deaths and $45 billion in damage. La Niña is the opposite phase. Trade winds strengthen. Cold water dominates the eastern Pacific. Global temperatures dip slightly. Australia gets its wet season. The Sahel and East Africa fill their rivers, and the American Southwest dries out. And this system, the El Niño-Southern Oscillation, or ENSO, is not a side note in climate science. It is the single most powerful year-to-year driver of weather variability on Earth, more influential than any storm, any volcano, any local weather pattern. When ENSO speaks, the entire planet listens, which is exactly why what's happening right now is so unsettling. The La Niña that developed in late 2024 and stretched into 2025 was weak from the start, weaker than scientists expected. It formed late, sat at the margins of what even qualifies as a La Niña event, and began fading earlier than almost any La Niña on record. And because it was so weak, the usual signals never clearly arrived. California's drought never materialized. The atmospheric rivers, enormous rivers of moisture flowing through the sky, thousands of miles long, kept coming anyway. It's because they don't take direct orders from ENSO. They are influenced by it, but not controlled by it. And with La Niña too feeble to deflect them, they hit California head-on, one after another. In Australia, the story was different, but just as strange. La Niña is supposed to bring Australia a wet, slightly cooler season. The rains came in some places, but the heat didn't leave. Temperatures across much of the continent stayed well above historical averages for a La Niña period, breaking records that had stood for decades. So here's the question that climate scientists are now asking out loud. Is La Niña losing its power? The answer requires understanding something that the raw data makes unavoidably clear. The planet's baseline temperature, the floor from which everything is measured, is now over 1.2 degrees Celsius, higher than it was in the pre-industrial era. That number sounds abstract. It is not abstract. It is the difference between a La Niña that cools the planet and one that merely slows the warming. Think of it this way. La Niña's job is to redistribute heat, to pull warm water west, let cold water rise, and take some thermal pressure off the global system. For most of human history, that job was enough. La Niña years were genuinely cooler. You could see it in the data as clearly as a dip on a graph. But in 2021 and 2022, the last significant La Niña period before this won global temperatures still broke records. Not as extreme as El Niño years, but records nonetheless. La Niña was doing its job. It just wasn't enough anymore. Because here's what changes when the baseline rises. Everything that depends on relative temperature shifts. Drought isn't just about how little rain falls. It's about how fast the ground dries out and a warmer atmosphere evaporates moisture. That means La Niña's droughts are becoming more intense, not less, even when La Niña itself is weak. And La Niña's floods, when they come, hit harder. The engine is the same, but it's now running inside a hotter room, and that changes everything it produces. Now here's where the story gets urgent. Climate models, which have become dramatically more accurate over the past decade, are signaling a meaningful probability that a moderate to strong El Niño will develop in late 2026. If that happens, the consequences will not be ordinary. El Niño on its own is already the most powerful short-term warming force in the climate system. The 2015-16 El Niño pushed global average temperatures to 1.5 degrees Celsius above pre-industrial levels for the first time in recorded history. That was treated as a landmark, a line scientists had long worried about crossing. An El Niño arriving in 2026 would not be arriving in 2015's world. It would be arriving in a world already running hotter. Scientists who study this trajectory have published projections suggesting that if a strong El Niño develops in late 2026, the year 2027 could see global average temperatures that would make every previous record look modest. What does that mean in practice? Mass coral bleaching events at a scale the ocean has not seen. Wildfire seasons in California, Southern Europe, and Australia that begin earlier, burn longer, and resist containment. Monsoon failures across South Asia affecting food security for hundreds of millions of people. Or Arctic sea ice reaching extent minimums that would have been considered impossible 20 years ago. And critically, feedback loops. As ice melts, it stops reflecting sunlight back into space. As permafrost thaws, it releases methane. As ocean temperatures rise, they absorb less CO2. Each of these processes accelerates the others. That's not speculation, that's physics. But here's what doesn't get said enough. We have never understood this system better than we do today. A global network of nearly 4,000 ocean monitoring buoys, the Argo float system gives scientists real-time data from the deep Pacific that didn't exist 20 years ago. New generation satellites can measure sea surface temperatures to a precision of a fraction of a degree. AI-assisted climate models are now producing ENSO forecasts 12 to 18 months out with accuracy that would have seemed impossible a decade ago. That matters because time is the resource that saves lives. When a drought is forecast 6 months in advance, governments can pre-position food aid, water managers can fill reservoirs before dry season locks in, farmers can shift to drought-resistant crops, emergency services can train and stage. The 1997 to 98 El Niño killed tens of thousands of people partly because it caught the world off guard. Yet the tools we have now would have seen it coming nearly a year in advance. Science has not solved climate change, but it has given us something genuinely valuable, the ability to see what's coming. Not perfectly, not with certainty, but early enough to act. ENSO has been cycling through this planet's climate for millions of years. It shaped the rise and fall of ancient civilizations. It determined which regions could sustain agriculture and which couldn't. It will keep cycling long after every human on Earth today is gone. But the world it operates in is not the same world it evolved in. La Niña is not broken. The physics still work. The trade winds still blow. The cold water still rises. What's broken is our assumption that the past is still a reliable guide to the future. The patterns we built cities around, designed water systems for, planted crops to match, those patterns are shifting, not disappearing. Shifting, becoming less predictable, swinging harder between extremes, arriving at the wrong time, in the wrong place, with the wrong intensity. That is the actual story of the 2025 to 2026 La Niña. Not just that it was weak, but that its weakness is a signal, one in a growing sequence of signals that the climate system's response to human-driven warming is accelerating. And if there's one thing history teaches about signals, it's this. The ones you ignore always end up being the ones that mattered most. If this raised questions for you what a 2026 El Niño could actually look like, how sea level rise interacts with storm surge, or what the jet stream's behavior means for your part of the world, those answers exist, and they're worth understanding. Read the primary sources. Check the NOAA ENSO tracker. Follow the WMO climate bulletins. Look at the actual papers, not just the headlines. The more people who understand these systems at a real level, the harder it becomes to ignore what they're telling us. And if someone you know needs to understand what's actually happening to the climate, not the politics of it, the physics of it, send them this, because the physics doesn't care what you believe.